The integumentary system, comprising our largest organ, the cutaneous membrane, plays a vital role in maintaining human health and well-being. Comprising two distinct layers, the epidermis and dermis, the skin serves as a protective barrier, regulates body temperature, and provides a foundation for various accessory structures. The epidermis, the outermost layer, forms a waterproof barrier and contributes to skin tone, while the dermis lies beneath and houses tough connective tissue, hair follicles, and sweat glands. Beyond its protective functions, the skin also serves as a reservoir for blood, facilitates excretion and secretion through sweat glands and sebaceous glands, and enables cutaneous sensation, allowing us to perceive touch, pressure, temperature, and pain. The integumentary system's significance extends beyond its immediate functions. It accounts for 7% of body weight, highlighting its substantial size and profound impact on our overall health. Synthesis and storage of nutrients. When exposed to UV radiation, the skin synthesizes vitamin D3, which is crucial for calcium absorption and bone health. Integumentary structures. The integumentary system comprises the skin and its accessory structures, including hair, nails, and glands. The skin throughout life epidermis develops from embryonic ectoderm. The ectoderm is one of the three primary germ layers in the developing embryo, giving rise to the skin, nervous system, and other structures. Dermis and hypodermis develop from mesoderm. The mesoderm is another primary germ layer, responsible for muscles, bones, connective tissue, and the circulatory system. Melanocytes develop from neural crest cells. Neural crest cells are specialized cells that migrate throughout the embryo and give rise to various cell types, including melanocytes. The epidermis, 4 main cell types. Melanocytes, found in the basal layer, they manufacture and secrete pigment. Melanocytes produce melanin, the pigment that gives skin its color and protects it from UV radiation. Merkel cells, located in the basal layer, they are attached to sensory nerve endings. Merkel cells are touch receptors that detect light, touch, and pressure. Keratinocytes originate from the deepest layer of the epidermis and migrate to the stratum spinosum. Keratinocytes are the most abundant cell type in the epidermis, producing keratin, a tough, fibrous protein that gives the skin its strength and resilience. Keratinocytes also produce antibodies and enzymes, indicating their role in immune defense and other biochemical processes within the skin. Additionally, keratinocytes become dead, flattened cells that form the protective outer layer of the skin through a process called keratinization. Langerhans cells, found in the stratum spinosum of the epidermis, are immune cells that play a crucial role in defending the body against infections by engulfing and eliminating pathogens. The epidermis, the outermost layer of the skin, is composed of multiple layers of flattened, scale-like cells. Each layer has its own specific function and cell types. The palms and soles, which are in constant contact with the environment, require extra protection and are therefore covered by a thicker layer of skin consisting of 5 layers. The remaining body skin, which is thinner, has 4 layers. The layers of the epidermis are arranged from deepest to most superficial as follows. Stratum basale, the deepest layer of the epidermis, attached to the underlying dermis. It anchors the epidermis to the dermis and contains stem cells that actively divide to replenish the cells of the epidermis. Merkel cells, associated with sensory nerve endings, and melanocytes, which secrete the pigment melanin, are also found in this layer. Stratum spinosum, This layer gives the epidermis its spiny appearance due to artifacts of histological preparation. During preparation, the cells shrink, causing them to pull apart, leaving behind spiny projections where they were once connected. The stratum spinosum contains thick bundles of intermediate filaments, composed of keratin, which provide strength and support to the cells. Inner filaments resist tension and contain a protein called prekeratin. Additionally, the stratum spinosum contains star-shaped Langerhans cells. Stratum granulosum. This layer consists mainly of keratinocytes, which are cells that produce keratin. The stratum granulosum contains inner filaments and keratoiline granules, which help form keratin. These granules contain proteins that bind to keratin filaments, contributing to the process of keratinization. Lamellated granules, on the other hand, contain a waterproofing glycolipid that is released into the extracellular space, creating a waterproof barrier that prevents water loss from the skin. Stratum lucidum. This layer occurs only in thick skin, such as the palms and soles. Composed of a few rows of flat, dead keratinocytes, the stratum corneum is the most superficial layer of the skin. It consists of dead, flattened cells that are abundant in keratin, a tough, water-resistant protein that provides protection against abrasion and penetration. Melanocytes, found in the stratum corneum, produce melanin, a pigment that gives skin its color. Tyrosin, an amino acid, serves as a precursor for melanin synthesis. Melanin absorbs UV radiation, protecting skin cells from damage. Variations in melanin production and distribution contribute to the wide range of human skin tones. Carotene, a pigment found in many fruits and vegetables, contributes to the orange-yellow color of the skin. It accumulates in the stratum corneum, giving the skin a yellowish tint. Hemoglobin, a blood pigment, is present in Caucasian skin and allows the crimson color of blood to show through. In individuals with fair skin, the pink or reddish hue of blood vessels in the dermis is more visible due to the lower melanin concentration. The dermis, the second major layer of the skin, provides mechanical strength, flexibility, and protection for underlying tissues. It is composed of tough connective tissue containing collagen and elastin fibers that give strength and flexibility. The dermis is highly vascular and contains various sensory receptors that provide information about the external environment. Blood vessels in the dermis supply nutrients and oxygen to the skin and help regulate body temperature. Sensory receptors detect touch, pressure, temperature, and pain. The dermis consists of two layers, the papillary layer and the dermopapillae. The papillary layer includes dermopapillae, which are the superficial layer of the dermis containing loose connective tissue and blood vessels that nourish the epidermis. The dermis, the deeper layer of the skin, is composed of three main layers, the papillary layer, the reticular layer, and the areolar layer. The papillary layer, the outermost layer of the dermis, lies beneath the epidermis and is named after the dermopapillae, finger-like projections that extend upward from the dermis into the epidermis. These papillae increase the surface area for nutrient exchange and anchor the two layers of the skin together. The areolar layer, the middle layer of the dermis, is composed of loose, connective tissue that provides flexibility and movement. It supports and nourishes the epidermis, provides sensory nerves, lymphatics, and capillaries, and blends into both the papillary layer above and the subcutaneous layer below. The reticular layer, the deepest layer of the dermis, is a tough, dense, and fibrous layer composed of dense irregular connective tissue. This type of connective tissue provides strength and resists stretching in multiple directions. It contains collagen fibers that limit stretch and elastic fibers that provide flexibility. The reticular layer blends into both the papillary layer above and the subcutaneous layer below. The dermis also contains various accessory organs that originate from the epidermis and extend into the dermis. These include hair follicles, sebaceous glands, and sweat glands. Additionally, the dermis contains cells of connective tissues proper, such as fibroblasts, macrophages, and mast cells, which contribute to its structural integrity, immune defense, and wound healing. Furthermore, the dermis communicates with other organ systems through various pathways. The cardiovascular system provides blood vessels in the dermis that transport nutrients, oxygen, and waste products. The lymphatic system drains excess fluid and helps to defend against infection. The nervous system provides sensory receptors that provide information about the external environment, allowing for sensation of touch, pressure, temperature, and pain. Finally, the nervous system regulates blood flow and the activity of sweat and sebaceous glands. Dermopapillae, which resemble nipples, increase the skin surface area for nutrient exchange and anchor the epidermis to the dermis. Dermal ridges, found on the palms and soles, enhance grip and form fingerprints. The epidermis, the outermost layer of the skin, contains epidermal ridges, which are formed by the overlying epidermis following the contours of the dermal ridges. These ridges contribute to the formation of fingerprints. The dermal layer contains cleavage lines, which indicate the direction of collagen fibers in the dermis. These lines are crucial for surgeons to consider during incisions. Dermal lines, visible patterns in the skin, reflect the underlying arrangement of collagen fibers. Figure 5.4 on page 155 likely illustrates the various dermal modifications discussed earlier. The subcutaneous layer, also known as the hypodermis, is composed of loose connective tissue, primarily consisting of areolar and adipose tissue. Areolar connective tissue provides flexibility and allows for movement, while adipose tissue stores energy and provides insulation. The subcutaneous layer also stabilizes the skin's position and is loosely attached to both the dermis and muscle. These loose attachments enable the skin to move independently of underlying structures. The subcutaneous layer contains numerous fat cells, which provide thermal insulation, cushion underlying organs, and safely receive hypodermic needles. Accessory structures include hair, sebaceous glands, sudoriferous glands, and eccrine glands. Hair functions include maintaining warmth by trapping a layer of air close to the skin, reducing heat loss. Hair follicles are associated with sensory nerves that detect touch and movement, alerting us to the presence of insects on the skin. Nails serve various functions, including protection and sensory perception. Hair serves as a protective shield for the scalp, safeguarding it against physical trauma, heat loss, and sunlight. It acts as a barrier against injury, UV radiation, and heat loss. Hair is distributed across the entire skin surface, except for certain areas such as the palms, soles, lips, nipples, and portions of the external genitalia. These areas are specialized for specific functions like gripping and sensation and do not require hair. Hair is composed of filamentous strands of dead keratinized cells produced by hair follicles. Keratin, the same protein that makes up the stratum corneum of the epidermis, forms the basis of hair. It contains hard keratin, which is tougher and more durable than the soft keratin found in the skin. The type of keratin in hair is more compact and cross-linked, making it stronger and more resistant to wear and tear. The hair shaft is organized into 3 distinct layers: the medulla, the cortex, and the cuticle. The medulla, the central core of the hair shaft, is often absent in fine hairs. The cortex, which surrounds the medulla, contains pigment granules that give hair its color. The cuticle, the outermost layer, is a single layer of overlapping cells that protects the cortex and enhances the hair's shine. Melanocytes, cells that produce melanin, transfer melanin to the keratinocytes that form the hair shaft, giving hair its color. The hair follicle, an invagination of the epidermis that surrounds the hair root, plays a crucial role in hair growth. The deep end of the hair follicle expands, forming a hair bulb, which is the base of the hair follicle, where cell division occurs, producing new hair cells. The papilla, a nipple-shaped indentation with blood vessels and nerves, provides nutrients and oxygen to the growing hair cells. Matrix, the germinal layer of actively dividing cells located right above the papilla. The matrix contains stem cells that give rise to the hair shaft and the inner root sheath. A knot of sensory nerve endings wraps around each hair bulb. Bending a hair stimulates these endings, explaining why our hairs act as sensitive touch receptors. This explains why we can feel even the slightest movement of our hair. Our arrector pili muscle, a bundle of smooth muscle, contracts to make hair stand erect, creating small bumps on the skin. This response is triggered by cold temperatures or emotional stress. Sebaceous glands occur over the entire body, except the palms and soles. Sebaceous glands are absent on the palms and soles because these areas don't require lubrication. Simple alveolar glands. These glands have a sac-like structure. Halocrine secretion. The entire cell breaks up to form secretion. Sebaceous glands release sebum by disintegrating entire cells. Sebum is an oily substance that most are associated with a hair follicle. Sebum is released into the hair follicle and travels to the surface of the skin. Functions of sebum: solvents and lubricates hair and skin. Skin waterproofing: sebum forms a protective barrier that prevents water loss from the skin. Collects dirt: sebum traps dirt and debris, helping to keep the skin clean. Sweat glands. There are 2 types. Eccrine, the most abundant sweat gland, also known as true sweat. Apocrine, odorous secretion. Apocrine sweat is initially odorless but becomes odorous when bacteria on the skin break down its components. Apocrine sweat is absent before puberty. Reline thermoregulation: evaporation of sweat from the skin helps to cool the body. Widely present in the skin. Present in the axillary, areolar, anal, and genital areas. These areas are associated with body odor. Nails, which are skull-like modifications of the epidermis made of hard keratin, are composed of the same substance found in hair. The nail consists of several parts: the free edge, which extends beyond the fingertip; the body, which is a dense mass of keratinized cells attached to the nail bed; and the root, which is the portion of the nail embedded in the skin, under the nail fold. Nail folds are folds of skin that overlap the sides and base of the nail. The eponychium, or cuticle, is a thin layer of skin that overlaps the base of the nail plate. Skin injury and repair occur through 4 distinct stages. Inflammation. This is the body's initial response to injury, characterized by increased blood flow, redness, swelling, and the recruitment of immune cells to the site of injury. Scab formation. A scab is a protective barrier formed by dried blood and tissue fluids, helping to prevent infection. Cell division and migration. Epidermal cells migrate into the wound and begin to divide, replacing damaged tissue. Scar formation. Fibroblasts produce collagen fibers that fill in the wound, creating a scar. Burns are classified based on their severity. First-degree burn. Only the upper epidermis is damaged, resulting in redness and pain. Second-degree burn. The upper part of the dermis is also damaged, causing blisters and skin healing with minimal scarring. Third-degree burn. The entire thickness of the skin is consumed, resulting in a white, red, or blackened burned area. These burns are the most serious and often require skin grafts for healing. The rule of nines is a method used to estimate the percentage of body surface area affected by burns. Aging of the skin is characterized by several major changes. Injury and infection increase. As we age, the skin becomes thinner and more fragile, making it more susceptible to injury and infection. Immune cells decrease with age, weakening the skin's ability to defend against infection. Sun protection diminishes as melanocyte activity declines, reducing the skin's natural protection against UV radiation. Skin becomes dry and scaly due to decreased sebaceous gland activity. Hair thins and grays as hair follicle activity declines. Sagging and wrinkles occur as collagen and elastin fibers break down. Heat loss decreases, and repair slows, delaying wound healing. Effects of UV radiation. Beneficial effect. Activates the synthesis of vitamin D3. Harmful effects. Sunburn. UV radiation damages skin cells, causing inflammation and redness. Wrinkles and premature aging. UV radiation accelerates the breakdown of collagen and elastin fibers. Malignant melanoma, a type of skin cancer that develops from melanocytes. Basal cell carcinoma, a type of skin cancer that develops from cells in the basal layer of the epidermis. Types and growth of hair. Vellus hairs, body hairs of women and children. These are fine, pale hairs that cover most of the body. Terminal hairs, hair of the scalp, axillary, and pubic areas. These are coarser, darker hairs that develop in response to hormonal changes. Hair thinning and baldness. Due to aging, hair follicle activity declines with age, leading to hair loss. Male pattern baldness, a genetic condition causing hair loss on the scalp. Skin cancer. Basal cell carcinoma, least malignant and most common. This type of skin cancer rarely spreads to other parts of the body. Squamous cell carcinoma arises from keratinocytes of the stratum spinosum. This type of skin cancer is more aggressive than basal cell carcinoma and can spread to other parts of the body if not treated. Melanoma, a cancer of melanocytes. The most dangerous type of skin cancer, melanoma, is highly aggressive and can spread rapidly to other parts of the body. The muscular system is responsible for movement in the human body. It consists of bones and joints, which provide the framework for movement, but they cannot move on their own. The human body has over 600 individual muscles that are responsible for a wide range of movements, from the smallest eye movements to the most powerful movements of the limbs. Muscles cause bones and supported structures to move by alternating between contraction and relaxation. During contraction, muscles pull on bones, causing them to move. Relaxation of the muscle allows the bone to return to its original position. There are three main types of muscles: skeletal, smooth, and cardiac. Skeletal muscles are attached to bones by tendons and cross joints. When they contract, the bones they attach to move. Skeletal muscles are responsible for voluntary movements of the body. Smooth muscle is found on the walls of internal organs and contracts to produce movement of organ contents. Smooth muscle is found in the walls of internal organs such as the digestive tract, blood vessels, and urinary bladder, and is responsible for involuntary movements. Cardiac muscle is found only in the heart and is responsible for pumping blood throughout the body. In addition to their role in movement, muscles also play a crucial role in stability and control of body openings and passages. Muscles surrounding joints help to stabilize them, preventing dislocation and injury. Small muscles hold vertebrae together, stabilizing the spinal column. Muscles along the spine help to maintain posture and stability. Sphincters, valve-like structures formed by muscles, control the movement of substances in and out of passages. For example, a urethral sphincter controls the movement of urine. Sphincters are circular muscles that contract to close openings and passages. Muscles have several functions, including heat production. When muscles contract, they release heat, which helps the body maintain a normal temperature. For example, when you're cold, moving your body can generate heat, making you warmer. Muscles also have several properties, including extensibility, conductivity, contractility, elasticity, excitability, and the ability to be cardiac, smooth, or skeletal. Irritability refers to the ability of a muscle to respond to a stimulus, such as an electrical or mechanical impulse. This response can result in tension development, but it may not always lead to a visible contraction. Skeletal muscle is organized structurally in a way that allows for efficient contraction and relaxation. The human body comprises approximately 434 muscles, accounting for around 40–45% of its total weight in adults. These muscles are responsible for bodily movements and maintaining posture, with 75 muscle pairs being particularly crucial. Skeletal muscles, which make up a significant portion of the body's weight, are essential for movement and posture. They are one of the 4 primary tissue types in the body, alongside epithelial, connective, and nervous tissue. Each type of muscle tissue has a unique structure and function. The skeletal muscles are composed of muscle tissue, connective tissue, blood vessels, and nerves, all working collaboratively to produce movement. The connective tissue coverings surrounding skeletal muscles include fascia, which covers the entire muscle and separates it from other muscles. Tendons, which are tough, cord-like structures made of fibrous connective tissue and connect muscles to bones. Aponeuroses, which are broad, flat sheets of connective tissue that attach muscles to other muscles or muscles to bones. Epimysium, a thin covering that surrounds the entire muscle. And perimysium, connective tissue that divides muscles into sections called fascicles. Endomysium, a connective tissue covering that surrounds individual muscle cells, plays a crucial role in supporting, organizing, and protecting muscle tissue. At the ends of muscles, the endomysium, perimysium, and epimysium merge to form connective tissue attachments to the bone matrix, known as tendons or aponeuroses. Skeletal muscle fibers, which are elongated cells capable of extending the entire length of the muscle, develop through the fusion of mesodermal cells called myoblasts during embryonic development. These myoblasts fuse together to form multinucleated muscle fibers, which become very large and contain hundreds of nuclei, making them multinucleate. The high metabolic demands of contraction necessitate the multinucleate nature of muscle fibers, which also contain satellite cells, stem cells that can differentiate into new muscle fibers and aid in muscle repair and regeneration. Microscopically, skeletal muscle fibers consist of a generic cell, the muscle cell, which shares many basic structures with other cells, but also has specialized structures that enable contraction. The organization of skeletal muscle tissues is characterized by the long, multinucleated, and striated nature of skeletal muscle fibers, which is a result of the arrangement of their contractile proteins. Skeletal muscle fibers contain several key components, including the sarcolemma, sarcoplasm, nuclei, mitochondria, myofibrils, and myofilaments. Sarcomere, the functional unit of muscle contraction, comprises repeating units of actin and myosin filaments. Z-lines mark the boundaries of the sarcomere, while the N-line serves as its center. The A-band houses thick filaments, and the I-band contains thin filaments. Within the A-band lies the H-zone, exclusively composed of thick filaments. The arrangement of myofibrils and sarcomers within a muscle fiber gives it its characteristic striated appearance. The sarcolemma, the cell membrane of a muscle cell, surrounds the sarcoplasm. A change in transmembrane potential initiates muscle contractions. When a muscle fiber is stimulated, the sarcolemma depolarizes, triggering a series of events that lead to muscle contraction. To produce a coordinated contraction, all regions of the cell must contract simultaneously. To facilitate this, the depolarization must spread rapidly throughout the entire muscle fiber. Transverse tubules serve as extensions of the sarcolemma that penetrate deep into the muscle fiber, enabling the depolarization to spread swiftly. These tubules facilitate the contraction of the entire muscle fiber by sharing the same properties as the sarcolemma and being filled with extracellular fluid. Myofibrils, which have a diameter of 1-2 micrometers, are lengthwise subdivisions within the muscle fiber. They consist of bundles of contractile proteins called myofilaments. Myofilaments are responsible for muscle contraction, and there are two types of myofilaments, thick filaments and thin filaments. Here are your annotated notes with explanations. Joints, also known as articulations or arthroses, are the points of contact where two bones, bone and cartilage, or bone and teeth meet. These joints enable our bodies to move in various ways. Essentially, joints serve as the connections that allow for movement or stability within the skeletal system. Joints can be classified into three main types based on their movement capabilities. Immovable joints. These joints are immovable because they are sutured together by connective tissue, providing strong connections for protection. For instance, the skull is composed of immovable joints. Slightly movable joints. These joints have limited movement due to the presence of fibrocartilage or hyaline cartilage connecting the bones. They offer both stability and flexibility, as seen in the vertebrae and the joint between the ribs and sternum. Freely movable joints. These joints, also known as synovial joints, allow for a wide range of motion because they contain a synovial cavity filled with lubricating synovial fluid. The synovial fluid minimizes friction between the bones, enabling smooth and pain-free movement. Classifications of joints. Joints can also be classified based on their structural features. Structural classification based on the presence-absence of a synovial cavity. Fibrous joints. These joints are immovable and lack a synovial cavity. They are connected by dense fibrous connective tissue. Cartilaginous joints. These joints are slightly movable and also lack a synovial cavity. They are connected by cartilage. Synovial joints. These joints are freely movable and are characterized by the presence of a synovial cavity. The synovial cavity allows for a wide range of motion. Structural classification based on the type of connective tissue. This classification helps us understand how joints are held together and their relative mobility. Functional classification of joints. Functional classification of joints is based on the extent of movement they allow. This classification directly relates to how the body moves and performs various actions. Types of freely movable joints. Saddle joint. This joint allows movement in multiple planes due to its unique shape. Both bones have concave and convex surfaces that fit together like a rider in a saddle. The carpal and metacarpal bones of the thumb form a saddle joint, enabling the thumb's wide range of motion, including opposition, which is essential for grasping objects. Ball and socket joint. The ball-shaped head of one bone fits into the cup-like socket of another, allowing movement in all directions. The shoulder and hip joints are examples of ball and socket joints. This type of joint enables us to move our arms and legs in a circular motion and rotate them. Pivot joint. This joint allows rotational movement around a central axis. The proximal end of the radius and ulna form a pivot joint, enabling us to rotate our forearm. This is crucial for activities like turning a doorknob. Hinge joint. Similar to a door hinge, this joint permits movement in a single plane, allowing for flexion and extension. The knee and elbow are examples of hinge joints. This design enables us to bend and straighten our limbs efficiently. Gliding joint. These joints have flat surfaces that slide or twist against each other. The wrist and ankle are gliding joints. They provide flexibility and allow the hands and feet to adjust to uneven surfaces. Condyloid joint. Similar to a ball and socket, but with more limited movement. These joints allow movement in different planes but not rotation. The joint between the radius and carpal bones of the wrist is a condyloid joint, enabling wrist movements like flexion, extension, abduction, and adduction. The significance of synovial joints. Synovial joints are covered with hyaline cartilage, which provides a smooth, low-friction surface for movement. They are held together by a fibrous joint capsule lined with a synovial membrane. This capsule provides stability and prevents dislocation. The synovial membrane secretes synovial fluid, which lubricates the joint, reduces friction between the bones, and nourishes the cartilage. This is why our joints can move smoothly and without pain. Tough, cord-like structures called ligaments hold bones together within the joint, providing additional stability. Joints can perform various movements, including flexion, decreasing the angle between two bones, like bending the knee. Extension, increasing the angle between two bones, like straightening the leg. Abduction, moving a limb away from the midline of the body. Adduction, moving a limb towards the midline of the body. Rotation, turning a bone around its axis, like turning the head. Supination, rotating the forearm so the palm faces upwards. Pronation, rotating the forearm so the palm faces downwards. Circumduction, moving a limb in a circular motion. Inversion, turning the sole of the foot inwards. Dot.